Okay, so welcome back, everyone. What I want to cover today is the differential amplifier. So we're going to jump back over to op-amp circuits. However, I wanted to introduce the digital to analog converter, since that's a building block for creating an analog digital converter. And then this next op-amp circuit is particularly well suited for signal conditioning of some value, some analog voltage, to feed it into an analog digital converter. Okay, and so that's why I wanted to have that basis so that we can kind of see the usefulness of this. And so this next op-amp circuit is the differential amplifier. Now, I should start off by saying that an op-amp intrinsically is a differential amplifier. What do we mean by differential amplifier? When we say differential, we're talking about the difference between two, in our case, voltages. So the difference between two voltages and the ability to also amplify the difference between those two voltages. And so we have that kind of intrinsically in our op-amp. If you think about it, take an op-amp, we have a non-inverting input, an inverting input, and when we give ourselves, say, 2 voltages here, let's just call this V in plus and V in minus, and you look at V out, we do have a difference between these two. V out is going to be equal to the open loop gain, AOL, times the difference between these two inputs. So you have Vn plus minus Vn minus. So we have a differential amplifier, is my point. Okay, the difference between these two multiplied by some gain, hence some amplification. However, as we already know by that asterisk mark that I had under those two rules for analyzing op-amp circuits, is that this value is very unwieldy. It is very large, 10,000. And so the usefulness of this op-amp as a differential amplifier is really quite limited. The only thing you could do with this is turn this into a comparator. So we're going to need to add some circuitry to really fully utilize this op-amp as a true differential amplifier, where we can adjust the gain and then take the difference between our two inputs. So that's what we're covering today. And then we'll see how incredibly valuable this can be when paired up with our analog digital converter for the sake of getting the analog world into our digital systems. Okay, so let's go ahead and put up the circuit for a differential amplifier. I'll call our first voltage V1. That's going to go into this resistor, which I'll call R1. And then we will branch off from here and go into our op-amp. Specifically, this is the inverting input. And we have an R1 and we'll have an R2. And then we have a second voltage that's coming in. This is going to go into our non-inverting input. So inverting, non-inverting input. And this value will also be R1. So if we pick 1K to be R1, similarly we'll pick our 1K to be over here for R1 as well. So these values are going to be the same. And then from this point over here, we'll have another resistor, and this one's going to be R2. So this is going to be the same value as this R2 that's up there. And then this is tied to ground, and we have some V out that comes as the output or the result of this. Now, what's going to be the equation for this circuit? It's going to be V out is equal to V2 minus V1 times R2 divided by R1. Okay, so as you can see, we do have the differential aspect taking place here. We have V2 minus V1, and that kind of makes sense because we have the V2 going into the non-inverting input and the V1 going into the inverting input. So I expect that it is a positive to whatever is connected to this, and a minus V1, which is what is connected to this. Okay, and then the gain is established by the ratio of R2 to R1. Okay, so let's go ahead and let's set up an example using this circuit. So let's go ahead and say we have a desired gain, a desired voltage gain, A sub V equal to 2. And if we want a gain of 2, then by this equation, we just need to have R2 be double whatever R1 is. So if R1 is 1K, R2 is going to be equal to 2K. Okay, and that's really all there is for setting up this circuit. Let's go ahead, draw this out, and put in some voltages, see what we get. So let's say for V1, I'm going to set that equal to, actually, let's plug these values into the top so I don't have to redraw this. So R1 is going to be equal to 1K. And R2 is going to be equal to 2K. And let's punch in some test values here. For V1, I'm going to make that equal to 1 volt. And V2 is going to be equal to, let's say, 3 volts. Okay, and so the question would be, what is V out going to be equal to? Well, we know that the ratio of R2 to R1 is 2, so we should have a gain there. And at this point, according to this equation, well, we're just going to take the difference between V2, so V2 minus, so 3 volts minus 1 volt gives us 2 volts. 2 volts times our gain of 2 is going to leave us with 4 volts. So this is what we should get. We should get 3 volts minus 1 volt times 2 equals 4 volts. Okay. And I think as far as setting up this differential amplifier and applying the equation, this is actually pretty simple, pretty straightforward. I think the nitty-gritty details is always in the application of this and why is this useful. Well, let's go ahead, let's establish a problem, a very common problem that pops up all the time when you're working with embedded systems and any type of analog voltage going into a computational device. And for that, let's go ahead and give ourselves an analog digital converter. Okay, and for my analog digital converter, I'm going to go with a very typical yet simple 8-bit analog digital converter with a 0 to 5 volt input. Okay, so let's give ourselves an ADC, 8 bits of resolution, and let's give ourselves a Vref equal to 5 volts. Okay, so since this is an 8-bit analog digital converter with a VREF of 5 volts, our analog voltage input range into this device is going to be one wire with 0 to 5 volts in, and that will get converted by this ADC each time a sample is taken into a digital output of discrete values from 0 to 255. Okay, so since we have only 8 bits of resolution, the number of discrete values we could get coming out of this ADC is going to be 2 to the 8th power. So 256 discrete values on the range of 0 to 255 base 10 or decimal, of course. Okay, and then the idea here is that this is either built into a microcontroller like an ARM processor or an 8051. Actually, I believe the 8051 currently being used in 262 has an analog digital converter built in, though that is not part of the original 8051 standard to have that. That is an extra peripheral that's been added by the manufacturer to make their device not only compatible with the 8051 architecture, but also to expand upon that and make their offering just a little more competitive. And nowadays, I would say almost all modern microcontrollers have at least one or two of these analog digital converters built in. So you may find that this part is built in to the device that you're using, your microcontroller or FPGA, or it is attached externally and then interface to the microcontroller or FPGA. Either way, this is the part that we're dealing with, and this is what we're, covering in this class. Now, to establish the problem that I want to show how to solve using this differential amplifier is the problem of scaling some input. So the idea here is you have some sensor that gives you a range, and you want to adjust that range to suit your application. Generally speaking, when you buy a sensor, that sensor is designed to be generic and cover a nice large range. So if we're talking about a temperature sensor, you want to be able to cover a lot of different temperatures, yet your application might want to focus in on only a particular range, not the entire range of that sensor. So for this, I'm going to use a current sensor. So let's go ahead and call this the problem. We want to measure current 0 to 10 amps. Now, why would we want to measure current? Maybe not a bad idea to talk about this. Okay, let's go ahead and set up something very familiar. Let's take a motor. And let's say our motor uses 0 to 10 amps. Now, one thing about motors is that the amount of current that they use, the way the motor appears as a load, that load changes, and it depends on how much torque it's having to put out. So, for my example, I'm going to go ahead and use an escalator. And this escalator has a motor at some point. I mean, at least I hope so. Okay, so you can think of an escalator as a conveyor belt of stairs. And off on the side somewhere, forgive my terrible drawing, you have some motor. As torque goes up, current goes up as well. And let's go ahead and say this is 10 amps and this is 0 amps. And so the more people you put on this escalator, the more current that motor is going to use. And if someone were to get stuck in this escalator, remember the whole thing of wearing sandals on an escalator and your mom telling you, watch out, don't get your flip-flops stuck in that escalator, because it's just going to, you know, pull your foot in and you're going to end up losing a leg or something. Okay. Well, when that occurs, your motor has to exert quite a bit of force to suck in your flip-flops into the escalator. And if you monitor the current consumption of this motor, you can detect this failure and then shut the whole system down for safety reasons. Okay, so this is done in practice. You monitor the current being used by this motor. In other words, current's important. It tells you something about this system. In our case, it tells you that someone got stuck in it. And so what we want to do is we want to measure the current. So we're going to use a current sensor. Okay, so that I can detect the situation when something bad is happening to this escalator. And I go to DigiKey, I go to Mouser, I go to my electronic components dealer of, you know, whatever company XYZ that I'm working with, and I say, go ahead, give me a current sensor. I need something that measures between 0 to 10 amps. And they're going to say, well, we don't have a 0 to 10 amp current measurement sensor, but what we do have is a -10 to +10 current sensor. And you go, hey, that's not bad. That's pretty close to my desired range. Most current sensors are designed such that they measure current not only going in one direction, which would be positive, but also going in the other direction, which would be minus. Because if I'm going to make a current sensor as a manufacturer, why would I make a part that's limited to only half of my values? So I go ahead and I purchase the closest sensor for my application. -10 amps to +10 amps, or 0 volts to 1 volt. Okay, so -10 amps is going to be 0 volts and +10 amps is going to be 1 volts, and all values on this range it's going to be linear. So if I had 0 amps, I would get 0.5 volts coming out of this sensor. Okay. And in fact, let's go ahead and let's write these down. Minus 10 amps. Oh, let's do I in. And let's do V out. From the perspective of the sensor. So minus 10 amps, we expect to get 0 volts. 0 amps, we expect to get 0.5 volts. And positive 10 amps, we expect to get 1 volt. Cool. Now you can see that there's a couple of things going on here already. Our analog digital converter is designed to accept 0 to 5 volts to convert that to 0 to 255 numeric value. 0 to 5 volts is well outside, or I should say, this is well inside that range. 0 to 1 volts. But not only that, our application that we want to use this for is going to only work 0 to 10 amps. So anything below 0 to minus 10 amps is pretty much unused. And anything between 0 to 10 amps is going to give us a difference of 0.5 volts, going from 0.5 volts to 1 volt. So let's just go ahead and what happens if we connect our sensor directly to this analog digital converter? If we just connect it directly, and then we map out what our discrete values are from this system, let's set that up as a table that we can do a mapping here on the right side. So our ADC to processor is going to take 0 volts to 5 volts and turn that into 0 base 10 to 255 base 10. So let's do V in and then I'll write over here is the converted value. Okay, well, our range is 0, so we'll start there. 0 volts gets converted into 0 base 10. Okay, what about 0 amps where we get 0.5 volts coming out of the sensor? Well, 0.5 volts gets converted to 26 base 10. And what about the case when the sensor is measuring 10 amps and it's giving the ADC 1 volt? Well, 1 volt gets converted to 51 base 10. And then outside of this range is no longer being covered by the sensor. In fact, this is all unused. So 2 volts, let's just put up some values here, gets converted to 102 base 10. And 2.5 volts gets converted to 128 base 10. And now we're at the halfway point of the range of our analog digital converter. And then we get 5 volts here, and 5 volts gets converted to 255. That's our full scale value. And so what is, for our application where we're only using 0 to 10 amps, what does that look like? Well, 0 amps gets converted to 26, and everything in between, and 10 amps gets converted to 1 volt, and so that turns into 51. And so I'm going to go ahead and call this my usable range. Everything below the value of 26 is unused. Everything above 51 is also unused. Now, I hope you see this as being a problem, which is that we're effectively taking our 8 bits of resolution that gives us this nice 0 to 255 range numerically output from here that we would, measure, monitor, run some program that does something to monitor these values. And if something were to go wrong and current goes up high, then we go ahead and trip the fail safe and turn the motor off, do whatever we want to bring this back down to a safe range. This effectively all we got is 26 to 51. That's nothing. How many values? I have, let's take 51 minus 26, 25. Okay, I got 25 discrete values. Of how many values total? 256. We have a possible 256 discrete values coming out of our analog digital converter, and because we're lazy and we just connected the current sensor directly to it, and we're like, hey, we'll just work with this in software. Well, we'll compensate for it, and we'll take that number and we'll go ahead and multiply it by some factor, and no. Because we've effectively chopped off most of the usable range of our analog digital converter. I cannot create values out of nothing. If you think about this is like almost like fidelity, like hi-fi versus lo-fi for your audio system. I should have 256 discrete values for my usable range, but instead now I only have 25 values. So if I take 25 and divide that by 256, great. I'm only using 10% of my ADC range. Only using 9.7% of my ADC range. This is so common. This happens all the time. And sometimes you can get away with it. And, it's just kind of a shoddy design. Sometimes you can get away with doing this, but more often than not, I would like to have my entire usable range. Everyone see this as a problem, right? Hopefully. Go ahead, type it in chat if you don't see this as a problem. They're like, this is perfectly acceptable to do. All right, I will take that as you completely see the problem at hand here. I don't want to go ahead and fix the problem until we accept that this is a problem. And I feel like this is, I've thought about this, this I feel like is the best way to demonstrate this issue. Just listing all the values and then showing the mapping from our usable range to what we're going to get actually coming out of this analog digital converter. Okay, so how do we fix this? With a differential amplifier. This is like the Swiss Army knife of signal conditioning for our embedded systems. It's simple to do. You're probably going to have to use an op amp anyways. You might as well add a couple of resistors in there, which is pennies, and solve this problem and get this right. Okay. So let's fix it. We need to scale this. Actually, there's two things we need to do. Let's talk about what we would desire to do here. Okay, so we're going to take our sensor. We're going to feed that into some block of signal conditioning. So that we get 0 to 5 volts coming out of this, going into our 8-bit ADC. So that we can get our maximum range of 0 to 255. Okay. Now, inside of this signal conditioning block, this is going to be created with a differential amplifier. Just calling it signal conditioning to keep it a little more generic. And here's our sensor. Okay, so what should our desired range be? Well, we want to go ahead and scale the sensor voltages. And in fact, we not only want to scale, but we want to provide an offset. You'll see this in a second. So our sensor is going to give us 0.5 volts to 1 volt. This is our used range, right? Because we're not using negative currents, we're only using positive currents, and we're taking it from 0 amps to 10 amps, and 0 amps gives us 0.5 volts, and 10 amps gives us 1 volt. So I'm going to write this off to the side just so that we can keep that in mind. And now what we want to do is for our ADC input, we want to change 0.5 volts to 0 volts, and we want to change 1 volt to 5 volts. And then as far as the numeric values that we will get from this analog digital converter, we will get 0 base 10 and 255 base 10. And so for our system, our intended range of current inputs, 0 to 10 amps, is getting perfectly scaled and offset to give us 0.5 volts to 0 volts and discrete value 0, and 1 volt to 5 volts, or 255 going into our microcontroller or processor or digital system, whatever it is. Cool. So can we convert this? What's in green is the important part. This is what we want our differential amplifier to do. Yeah, absolutely. We can set this up. Now, the easiest way to see this, I think, is by looking at that equation. So let's go ahead and let's say our differential amplifier equation is V out is equal to V2 minus V1 times R2 divided by R1. And I can further break this down into our R2 divided by R1 is our gain, and this is our differential voltage input. Now, my difference for my sensor input is 0.5 volts. 0.5 to 1 volt is a 0.5 volt difference. And I want to multiply that by some number to give me a 5 volt difference. Okay, so let's go ahead and say my delta V in times some gain needs to equal my delta input to my ADC. Or, in other words, delta V in times some gain needs to equal 5 volts. Actually, I should have written this out as 0.5 volts times some gain needs to equal 5 volts, right? I just use this notation to make this a little easier to see, because we're just talking about the difference between the input to the difference of the output. Okay, so this tells us our gain needs to be 10. And so what we have right now is half of our puzzle. Okay, we know that R2 divided by R1 is equal to our gain, and so we need R2 divided by R1 to equal 10. So let's go ahead and now establish that we know what our R2 and R1 should be. We can make R2 equal to 10K. We can make R1 equal 1K. And now we have a gain of 10 for our differential amplifier. Okay. And now what we need to do is we need to do the offset. So what I did over here was only do the scaling. We also need to do the offset. In other words, I need to take my 0.5 volts and convert that to 0 volts. And if we look at the equation, V2 minus V1, okay, so I'm going to take my voltage output from the sensor and I'm just going to subtract from that 0.5 volts. If I do that, then anytime I have 0.5 volts on my input, I get 0 volts on my output. Okay, so now I've gone ahead and I've established what V2 is supposed to be. V2 is my connection to my sensor, and V1 is a fixed 0.5 volts. Okay, so I actually now have everything that I need to set up my differential amplifier in order to convert my 0.5 to 1 volt into 0 to 5 volts. So let's go ahead and let's draw this. R1 we figured out was going to be 1K. R2 we figured out was going to be 10K. And this is all we have to do. So we have a fixed 0.5 volts. Now I'll go ahead and say fixed 0.5 volts. Feeding into our inverting input and our V sensor, which takes on a value of 0.5 to 1 volt, and that feeds into our non-inverting input, and this whole thing has a gain of 10. And if you remember the equation, V out is going to be equal to V2 minus V1. And I'll go ahead and write where V2 is over here. Times R2 divided by R1. And so let's go ahead and let's just look at the extremes. When my V sensor is at its lowest point, 0 amps, what do I get? And when my V sensor goes up to its highest point of 10 amps or 1 volt, what do I get for V out? So let's do the min case. Well, the min case is going to be of 0.5 volts in. V out is going to equal V2, which is 0.5 volts, minus V1, which is 0.5 volts, times R2 divided by R1, which is 10. And so we get 0 volts out, which is our minimum value that we wanted. And now the max case, V out is equal to, well, V2 is 1 volt now, because that's our max case of 10 amps into the sensor, minus a fixed 0.5 volts times 10. So 1 volt minus 0.5 gives us 0.5. 0.5 times 10 gives us 5 volts. Problem solved. All values in between here are linear. And so now we've gone ahead and we've solved our problem. Now we are using the entire full range, the entire 8 bits from 0 to 255 of our analog digital converter. And this is a much superior situation to be in than our terrible situation before, where we were only using 25 values of our possible range for this analog digital converter. Okay, so there were 2 things that we had to do to make this work. We had to do an offset to bring the 0.5 volts down to 0 volts, and we needed to apply some gain in order to change this scale from a 0.5 volt difference to a 5 volt difference. Okay, which is what I did over here when I solved for it. So we can do offset and scaling. Now, I find that 9 times out of 10, I have to do both offset and scaling in any consumer product or any industrial application that I've ever worked on in the past. I have been doing this for, let's see, 12, 13, 14, 15 years. I'm just getting too old. And every single device I've ever worked on that uses a sensor, I'll put that caveat in there. Any device I've ever made that uses a sensor ends up needing, 90% of the time, needs this in order to adjust the values so that I'm not sacrificing resolution of my analog digital converter. This is the right way to do it. Do I have any questions about this before I continue? Well, isn't that a loaded question? I always design to the requirements. Requirements are necessary. You really do need them to start off. That being said, every single requirements ends up with a nice conversation going back to the operation. You gotta have some flexibility when you're designing. But you can't be lost in the woods 24/7 either. Okay, so requirements are super critical. They are important, and you really should have some direction when you're approaching some design. So yes, you need requirements. I absolutely hate when I've worked, and I've worked in these environments where no one is setting up requirements for a design, and then you're almost done with it, or you've made significant progress, and all of a sudden it's like, oh, this isn't good enough. And I want to have those requirements as a fallback to defend myself in the workplace and say, well, the requirements said this, and this is absolutely fulfilling those requirements. But when you don't have requirements, then it's kind of assumed that you are just going to make it work. And I don't want to be in that position, because there's you can make it work and then it just kind of doesn't work that great, or it's over-engineered for the design. You're sacrificing too much when you're not trying to hit certain requirements. And at the same time, I think more so it comes down to, at least for me, yeah, in a perfect world, I'd love to have everything 100% spec'd out, and then I design to those requirements. But it comes down to a lot to just protecting yourself in the workplace. I want to know what it is that I'm shooting for, because if I just have a boss, manager or owner of the company, I've worked at a lot of smaller companies where, you're directly dealing with the owner. The owner's not that, savvy when it comes to engineering, and you kind of, oh, let's do this, and you're like, okay, but I can do, there's some compromises, I can do it this way, I can do it this way, and he just doesn't care, he just wants it done. And it's like, well, let's establish some requirements. And so I think it's important to protect yourself and protect your work by having requirements, and that's important. Yeah. Okay. What about, does this make sense to everyone? This is like, if you're going to get something out of this class. Okay. There is one other function. Yeah, which was the previous page? Are you talking about this page? I can 100% guarantee that on the final there will be a question asking for this of an op-amp. Asking for a differential amplifier. I will give you a sensor, and I will give you the resolution of an analog digital converter, and you will have to maximize that resolution, maximize the usage. So you're going to have to do this on the exam. Now, I think it's actually super quick to do. If you have a page of notes that just has your differential amplifier, and you look at this equation, you can figure out the values in order to fit any sensor to the usable range of your analog digital converter. Okay, so as far as, preparing for the final, this one is going to be in there. Now, there is another thing that you can do with this differential amplifier. So I said offset and scaling. Okay, by offset, you're setting one of these to be a fixed value. And for scaling, you're adjusting the ratio of R1 and R2 to give you your desired gain in order to take your delta V in and match it to your desired delta V out. There is one other function, and that's that I can also invert. I can take negative voltages and I can turn them into positive voltages. And the way you do that is by flipping which one of these is the fixed value. Okay, so if you look at the equation, I can very easily design this to take a negative, let's say instead of 0 amps being 0.5, it could be at 1 amp, and 0.5 volts could be 10 amps, and 1 volt could be 0 amps. So I could swap these. So you can also invert the direction by simply changing what is being subtracted from what. Okay? So I can make it so that the fixed 0.5 volts is being subtracted by 1 volt. And that's going to go ahead and account for the direction of this. So offset, scaling, and also inversion. So that's just so powerful of a little circuit to be able to do that. Okay, and like I said, you're going to need an op amp in there anyways. if I go back to not even invoking the differential amplifier, if I go back to just taking my sensor, going into an ADC, this is generally a pretty bad thing to just directly connect them. And the reason for that is what is the impedance output of my sensor and what is my input impedance of this ADC. So even just connecting these two things together, you're left with this situation again, where my sensor has a Z source or a Z out, and my ADC has a Z in. Okay, and generally speaking, most analog digital converters that I've worked with in microcontrollers generally don't have that high of an input Z in. And so my sensor, generally speaking, also doesn't have that low of a ZS or a Z out. And so to get this right in the first place, I usually have to do this anyways. I'm going to say 9 times out of 10, I have to put a voltage follower in here in order to solve the problem of these impedances squashing my analog output from the sensor. So generally speaking, I need to do this anyways. And if I'm going to put 1 op amp in here, I might as well just put 2 op amps in here. I can feed the output from this op amp directly to the input over here. If you look at it, this is medium to high impedance. This is only 10K. Well, if you look at this here, we do have a pathway to ground of 1K and 10K, and assuming that this is 0 amps in or out of this input, this is pretty high impedance. And so I do have high impedance, but I also have some medium to high impedance here. So this can also affect, it will affect your signal because you're driving a 11K load essentially over here. So you're probably going to need a voltage follower in front of this to do this properly. And even if you were to connect the sensor directly to the ADC, you would still need this. And when you buy an op amp, usually you can get a little 8-pin package that has 2 op amps in it. So you're not helping yourself by not utilizing this circuit and not using a voltage follower. All you're doing is kind of the lazy approach of just willy-nilly connecting things and kind of hoping that it works, and that'll get you by academically, no doubt about that. Like, I see that all the time, just connecting, oh, it's sensor output, it's going into an ADC, and then you work on your software and you don't give this kind of stuff a second thought. But I'm just saying it's the lazy approach, and it's not going to cut it in the workplace. So please do yourself a favor, get comfortable with this circuit. This is not a hard thing to implement. We're just talking about 4 resistors and 1 op amp. You should use 1 op amp anyways as a voltage follower. Why not just do it properly? Okay. So I'm going to, that's it. That's the end of this semester.